something else. Like for instance, I have a Toyota Camry. Sometimes we don't call it a Toyota Camry. Sometimes I call it Bruce.
Bruce Willis.
No, actually my wife named it. She bought it brand new, and from earning like money babysitting when she was in high school.
Oh wow.
Yeah, and I inherited it after we got her a new car, so I got her old one. So that's why you see me driving the old Toyota Camry. Well, it's a good thing because it was brand new at one point. But anyway, we call it Bruce. Well, sometimes what you're going to find is that these legs are going to be called different names. So just put it in your mind. Sometimes they can be called different names. And we're going to go over that and why we would do that in a few minutes. What is green? What? Adjacent. Okay. So does everybody get that? Thumbs up, thumbs down. We're going to do it simple. Thumbs up, does everybody get that? If you don't get it, thumbs down. Okay. So, does everybody get the hypotenuse is always on the angle of a right triangle? You get that, right? Yeah, this is the hypotenuse. Everybody get that? Nobody wants to talk. Nobody wants to say yes to their own view.
Yeah.
Okay.
Indeed.
Now, this is the angle. That's the angle, yes?
Yes.
That's the angle, yes? So, if that's the angle, if you start out right here, anywhere that you go is going to be opposite of that point, right? And that's what makes this leg of the triangle the opposite. Okay? So let me erase what I just wrote so that way it makes sense. And let me just go ahead and get rid of all the colors now. Okay. So I'm going to make a nice straight line. Okay. So if you start out right here in this, on that corner of where the angle is, if you start out right here, what do they call that? They call that a vertex, where two plates come together. Vertex. Is that what they call that? I'm not a math person. Okay. If you start out there and you go out from the angle that you know, then that is the opposite right here. Is the opposite leg. Okay? That only leaves one other leg, and that's the adjacent. So this is the adjacent leg right here. Still the adjacent leg. Please don't do that. Okay. Now another way you can think of the adjacent. Adjacent means touching. Okay? So like for instance, if I have a home and it has a property line that touches another property line, it's adjacent to it. Okay? But it's always been easier for me to identify the hypotenuse, and then just think, where's the angle? It's just diagonal to it, and that's going to be the opposite. Because it's the opposite of it. Yes, yeah, it's always the one that has a slope. And on a right triangle, it's always the longest one, right? Okay. Thumbs up, thumbs down. Okay.
Why are we being recorded?
Because we have like 8 people out.
Oh, I know.
Yeah.
Being recorded? Hi, Shelby, Marina, Hannah.
Well, it's also for other people that's going on there too. Okay. Now. So listen. Knowing that, let's look over here at sine, cosine, and tangent real quick. So I'm going to use something I think it'll help. Because we don't know these legs as A, B, and C, do we? We know them as O, H, and A. So I'm going to just erase this. Okay, I'm going to cover it up. Right? Okay. What is these two? S, O, over H, so,
Oh, I understand that now.
oh, that's what I did too. Okay. That's going to be creepy sounding on here. that means that other people like assistant principals can listen to it too. Okay. So, first, third, second. Okay. So looking at this, we're given 42 meters per second for the hypotenuse. If I want to find what is the opposite, this one, I'm going to erase this out. If I want to find what is the opposite, which one of these three do you think I should use? I know an angle, and I know the hypotenuse.
Cosine.
Cosine?
Yes.
Okay, so I'm trying to find opposite, and I know the hypotenuse.
Something that you don't know.
It's like you can't use something that you don't know and tangent and sins and these.
Okay, so now wait, look. I'm trying to find opposite. Does cosine have opposite on there? No. Can I use it then?
Yes.
Why would I use something that's not going to yield the opposite? There's nothing I can do to get the opposite out of this, is there? This one doesn't have the hypotenuse. This is the one that has the hypotenuse, the angle, and the opposite. That's what I'm interested in. I'm interested in the opposite, finding the opposite, so that has to be there. I know the hypotenuse and I know the angle. So that means I have to use sine of the angle is equal to opposite over hypotenuse. You get it, Daphne? No. Okay. So what did you think we should do? Okay, so let's do something real quick. This will make it a little easier for you. Yes. That's theta. That means this angle. Okay? So this is what I want you guys to do. Just to make it a little easier, get a calculator. Get sine 35. We'll talk to it in another language. Okay, 0.5. What was it? That's good enough. That's equal to opposite over hypotenuse, right? Do you get it? Yes. That's good enough for now. That's good enough for now. But because these only have 266, and I'll show you later, but I wanted to put this out here because it'll give you a little bit better, a number that'll work out in a few minutes better. But boy, whenever I listen to this video later on, it'll work out a little better. That's why I want to use a little bit better of a number. Okay, that's nice circular reasoning. Okay. H is what? Hypotenuse. That's 42. So I'm going to erase the H here. And I'm going to put 42. The meaning of life. Now, how can I get the 42? How can I get O by itself?
Multiply by O on both.
Multiply by 42 meters per second on both sides, right? These divide out to be 0. So take 42 times 0.5735. Virginia, can you step outside? So the opposite leg, that's the one we're dealing with, that's what we just found, is equal to 24 meters per second. Right? So where are we at on that? You guys, 1, 2, 3, or 4?
Why did you do that number over 17?
Because I have something that writes it out exactly what I mean right over there. Okay, so let's go.
Why did you pick our class?
Because your class has everybody going in it. Okay. So let's look at this. Let's go on. Okay, so that dealt with this, with the opposite. Let's look at the adjacent. What you're going to find is the exact same steps we used for the opposite we're going to use for the adjacent. The exact same steps. So let's look at this. Easton?
What do we do with tangents other than the opposite?
We could, but it's better to just go ahead and stick with what? Cosine. So let's put this up. Since the adjacent, we know the adjacent. No, we're trying to find the adjacent. We know the angle, and we're trying to find the hypotenuse. Wait a minute. I need to take a drink of Diet Coke because I'm getting in trouble in a moment. What are we trying to find? What do we know? Hypotenuse and the angle. So, we're going to do cosine of the angle is equal to adjacent over hypotenuse, right?
Yes.
Everybody get that? So what are you going to do first? Cosine of the angle. What's the cosine of the angle? No, we don't. The cosine of 35 is what? 0.819. That's equal to adjacent over hypotenuse. But the hypotenuse, again, is still equal to what? 42. Do you get that? You understand this is the hypotenuse? Okay. So the hypotenuse right here, we're going to put it in, okay? So that's going to be 42 meters per second. So what are we going to do with that 42 meters per second? What are we going to do with 42 meters per second? How do we get this off this side? Here you go. So we're going to multiply both sides by 42 meters per second. That divides to 1, and you get what, Easton? 34 million meters per second, right? So we get the adjacent as 34 meters per second. Okay. How could you test this to see if it's right?
You can just fill out either of the other.
You could use Pythagorean theorem, right? You're going to find it's a little bit off because we have some rounding issues. Yes?
The hypotenuse.
Yeah. Okay.
That's how we got the
Yes. Yep. Because what you do to one side, you got to do it the other. That's called the golden rule. Right? Okay, so now what I'm going to do is I'm going to take a step back from this. We're going to do it all over again, the same ones. But now we're going to change a few things. Okay? We're going to just change how we do it and create a formula that you can apply to any vector like this that has its angle to the, what do we call this? What do we call this way? Is that the horizontal? The horizontal, right? So anytime you have an angle to the horizontal, you'll be able to apply this, right? Okay. So I'm going to know this is the hypotenuse. So we know that we're going to use, to find the opposite, we're going to use sine. So sine of the angle is equal to opposite over hypotenuse. Now to solve for opposite, what do we multiply both sides by? Somebody raise their hand and don't just yell it out. Yes, just a second. What is it? Not 42. Tell me the variable. H. What's your question? The what? The tangent? Yeah, you got it. That's the right thing to do. That train of thought is what I want you to have in physics. That one right there. Yes. Okay, so what I'm going to do is not put numbers in it just yet. We're going to wait until the very last moment to put numbers in it. Okay? Go, even if they ask questions, answer. Yep. We're going to multiply both sides by h. Okay. So we're going to multiply both sides by h. And then h drops off this side. So we get this handy dandy h sine of the angle is equal to O.
This was on the brain to me a while ago, and I had no idea what it meant.
Okay. Yeah, there's a brain genie where kinematics that it was on, right?
I was so confused.
Or no, yeah. Anyway. So let's look at this and let's decide something. This is the velocity, right? Meters per second, that's velocity. We're going to call that velocity, but this is the x direction on this side, right? That's x, so that's got to be velocity too, because we're talking about velocity over here, and this is going to be velocity. Look at that, I call that x. That's not x, and nobody fixed it. How come somebody didn't catch me on that?
Because we expect you to always be right.
I am old. Help me out. That's not x, that's y. I'm old. Old wins. Young. Evil. Okay. Watch.
Are you 50 years old?
Almost.
I'm 50. 52.
Okay. 47.
47.
Yeah. Okay. Actually, my wife and I debate how old I am. Okay. So, if this is dx and that's dy, what do you think we're going to call this? This both has x and y components. Right? No, we call that, it's both x and y, so we call it v x, y. You guys weren't even close, so I was like, I'm just going to go with it. Okay, yes. So the hypotenuse is 42 meters per second, but it's really the velocity in the x and y direction. Do you get that?
No.
Okay, so watch this. Whenever I throw this potato, if I throw it straight out, it only has velocity in the x direction, right? If I throw it straight up, it only has velocity in the y direction. But if I throw it at an angle, it has both. It has both. Okay, so do you get why that is x and y now? Okay, yes.
What I don't understand is why it's x times y, because it couldn't be that.
It's not x times y. This is denoting this is velocity in the x and y direction because it's a subset.
Cool.
It's like 100.
It's just a link.
Later.
Say sorry to the potato.
I'm gonna eat that potato later on.
No!
So, listen. Okay, so Vxy is the 42 meters per second. What did we find a while ago? We found both the adjacent and the opposite, which corresponded to Vy and Vx, right? So, how do we turn this equation into something that has usable terms? Well, h corresponds to what? So Vxy one corresponds to the opposite? Vy. Does everybody understand that? Okay. So real quick, find Vy. Using your calculator and sign. I bet somebody got it right now. Huh? Okay, so what's dxy? 42. What's the angle? What's theta? 35. Huh?
Did I do it right? Calculator.
Okay, so. Yep. Yep. Yipper. You got a yipper. Okay. Yes. Okay. So what? Your calculator hates you.
Yeah, it doesn't want to do what I need it to do. No. Every time I try to get to the sign,
The sin?
it comes up with some notification.
Okay, so watch. You should have, you can see it up on the board actually. You should put in 42, and then you'll navigate over here to the trig function. Sine 35, and hit enter. Yeah, this is dxy, sine of the angle. I wish I could make that sit up on top of everything. I wonder if I can. Well, because PowerPoint doesn't work that way. Oh, no. That'd be nice. Okay. This is in PowerPoint. Okay, so let's look at how to find dx now. Can anybody just look at that and go, this is, in this format, this is what it's going to be for finding dx?
I need your help.
What are?
Every time I try and go it works when you can't.
Well, because you don't have to do control.
I don't.
No.
Okay. Thanks.
You're welcome. Okay. So can anybody look at this and go, I get it, it's not going to be, this is what it is going to be. Define, that was defining dy, how do we find dx? How do we find the x direction? We know the y direction is this equation, how do we find the x direction?
Do we use tangent?
No. Okay. So let's look at it. Adjacent is going to be cosine, so it's going to be cosine of the angle is going to be equal to adjacent over hypotenuse. Everybody follow me on that? It's adjacent because that's what we're trying to find is the one that corresponds to dx. Then we're going to multiply by what? H on both sides. So now we have this equation. H cosine of the angle is equal to the adjacent. So what corresponds to H again? Which one of the velocities correspond to H? dxy cosine of the angle is equal to what? Adjacent corresponds to dx. Box around this. That's going to be a very important equation to you guys. So important that I got it over there.
Wow. Just saw that. It went from his mind to the wall. How does that work?
Right here. is the triangle we use. Okay, even though it's two vectors coming out that way, you really know that vector gets transposed over here to make a right triangle. Remember the word transpose? Everybody's like, what does that mean? That means you're going to move a vector to where you have it head to tail. Okay? So, now it's your turn. Now I want you to do these two. That is not a box, but that's okay. Okay, so what are we finding here? What did we find a while ago? We found their what? Components, right? Now let me talk to you why that's important. Real quick, before you do these two, I want all attention up here. Okay. So what we found was that dx was equal to, on this one, 24 meters per second. Can I erase some of this to make it a little more clear up here?
Yes, go ahead.
I'm going to erase the O's. We don't need this anymore. There we go. We don't really need that either.
You don't need any.
We just erase the class.
Yeah.
Okay. So, what did we find? By the way, this is coming up this direction. What did we find dx was? 34? 34, is that right, or 32? I think it's 34, right? 34 meters per second. And what did we find dy to be? 24 meters per second. Okay. So imagine, let's just do a little math here, or not math, a little thought experiment. Imagine that I launch this thing at 35 degrees to the horizon, and it's going 42 meters per second. Over here, I'll erase that too because it looks bad. There's too much. Over here, it's going to land at 42. Whoops, that's not right. Oh, it's supposed to do that. There. Now, I'll edit that out. At what speed does it land at? What speed? If it launches at 42 meters per second, how fast does it land? There we go. 42 meters per second. At what angle does it land at? 35 degrees. That's symmetry, right? You guys remember reading about symmetry?
Yep.
Out in kinematics too. Whatever angle I throw this potato at, heads up.
Do not. The potato!
Whatever angle I tried to throw the potato at, it's going to land at that same angle, right? If it's at the same height. Now, obviously, if I throw it up here, it's going to come down. It's going to land at a different angle, right? But if I throw it like this, it's going to go. And it's going to land at that same height with the same velocity, negating air friction. Yes. Somebody's gone right now. He's taking the restroom pass. Okay. So, the other thing that I want to drive home here is if I throw it at 42 meters per second, it's going 42 meters per second. Let's say I throw it straight up at 42 meters per second, right? What's its y velocity or its x velocity? If I throw it straight up at 42 meters per second, what's its x velocity? 0. And if I throw it straight out at 42 meters per second, what is its y velocity? 0. And then, so somewhere in here, it starts to change its x and y velocities, right?
Yeah.
But if I throw it at 35 degrees and 42 meters per second, what is its x velocity? How fast is it going along the horizon? What is it?
34 meters per second.
per second. Does everybody get that? That's what we just found. That's what it means by finding the components. Now, knowing that, if I throw this and it stays in the air for 1 second, how far does it travel downrange? How far does it travel? Not 42 meters. How far does it travel in the x direction?
34 meters.
34 meters, right? How far does it travel after 2 seconds?
68.
How far does it travel after? No, I'm not doing that. Very good, Ethan. Okay, is that right? I don't know. Okay. So really, what formula are you using there? When you're doing that, you're using what formula, Ethan? You're using this formula. Velocity, well, it's really average velocity, is equal to distance, a change in distance, over a change in time. And in your head, you're doing that equation. How are you doing that? Well, you're multiplying both sides by what? I'm asking for distance. You're doing what?
Oh, you're multiplying by
Delta T. Right? So, 34 meters per second times 2 seconds is equal to 68 meters because the seconds cancel. Do you follow me on that?
Sure.
Okay. So the point of this is to help you guys get ready to work with these kinds of equations in a more simplistic manner. If I gave you this question and didn't tell you how to get the x's and y's, it'd be too much. You were missing a step, but now you have the step to get the x's and y's, right? And then you're using a simpler equation, v is equal to d over t, to determine the distance that it travels in the x direction. Yes?
Well, why do we need to know the x's and the y's? We can just use, like, if it's a hypotenuse.
If it's a height. Say it again.
Like, why do we need to know, like, why do we need to translate it to vxy or vy or vx?
Well, we start out at, I don't know why that said vx, that should say vxy. We start out at vxy. Before we can find the distance that it travels, given 2 seconds, you got to know how fast is it traveling
No, that's not my
in
question.
this direction.
My,
Yes.
my question is, why do we need to use those variables when we could just use h, o, and a?
Well, I'm glad you asked. Because is this the only thing we're ever going to apply to? No. In fact, if you look at the next question, B, what's the hypotenuse in B?
20 meters per second.
20 meters per second squared. What's that giving you?
Acceleration.
Acceleration. So now, we're taking generically, you already know O, H, and A, which we had applied to velocity, and now how are we going to apply it? Instead of velocity, it's going to be what? AXY. Sine of the angle is equal to AY. AXY cosine of the angle is equal to AX. And that should all be like sub x. What's the next one? It's meters. What's it measuring? Distance. Delta D. So instead of A, it's going to be D. Right? So does that make more sense now? So what she is saying is absolutely right, except, well, it's setting you up for a win later. You have to know the O, H, and H. You have to know those. You have to understand why they are what they are. But ultimately, most of the time, you're going to be using one of those two variants of equations, but there's still at least 4 other equations that we're going to have to use for trig. But once you get these two down, the other 4 are very easy. The tangent one, once you get these two down, There's only one situation where you have to use tangent. There's a bunch of situations where you have to use inverse sine, inverse cosine, inverse tangent. Okay? It just undoes and gives you back the inverse by knowing these two numbers, or these two numbers, or these two numbers, you get the inverse of sine, inverse of cosine, inverse of tangent, and you get the angles. That's where you use the inverse. Okay, that's actually further than what I've gone over my classes. I've not mentioned that in any other class yet.
Oh, we're so smart.
That's it. Okay. So, what I want you guys to do, I'm going to erase some. I'm not going to erase everything, but I'm going to erase this right here so you guys can get a little closer look at what's going on. Okay? That's just, it's like a Greek letter theta. It's because we're running out of letters, so we have to, go back in time. There's a backwards E?
No, I don't see it there.
Oh, the sum. Yeah, okay, so we're going to use that today, too. That one? That's the sum. Okay. So, real quick, I want you to do these two questions, but what I want you guys to do, consider first, is that positive or negative right there? Positive. Is this positive or negative here? Negative. Is this positive or negative here?
Positive.
Is this positive or negative here?
Negative.
Okay. When you're doing it, oops. Don't worry, they're just 145 cents pocket change. Well, not for me, but I mean for Easton. Guys, I want you to find, on this one, I want you to find AX and AY. On this one, I want you to find DX and DY. Do that now. Well, then you might find the fact that I might. Ooh, I'm on recording. I can't say that.
Oh!
I'm going to stop. How many grades you going to give yourself? No, that's right. It's okay. Okay, so now we're going to go on to the next question. But before we do, this is where having a video camera would be nice because they don't get to see it. If I'm going to roll this chair across the floor, if I start out at 2 meters per second and I gradually increase to 10 meters per second, what is my average velocity? I'm going to, okay, so how did you find that? I gradually increased from 2 to 10, right?
399.
Okay. So I went from 2 meters per second to 10 meters per second. How do I find my average velocity?
Divide the
So,
2.
it's literally the initial velocity plus the final velocity divided by 2, correct? Okay. So I'm going to write that on the board over here so you guys can just keep that in mind. Okay, so it's, guys, would you mind reading the question to me?
A train accelerates from a velocity of 4.0 meters per second to 27 meters per second in 13 seconds. How far does the train travel at a given time? Draw a three-body diagram of the
Just a second, Easton. I want to make sure everybody's paying attention. Go ahead and run it, but let's make sure everybody's paying attention because this is going to be a doozy if you're not, okay?
Can you
Okay.
scan it? Can you scan?
Okay, so, Easton, go ahead and reread it.
A train accelerates from a velocity of 4 meters a second to 27 meters a second in 13 seconds. How far does the train travel at a given time? Question mark. Draw a three-body diagram of the train and remove the friction.
Okay. So, tell me what I need to highlight. Tell me what I need to highlight here. A train accelerates from a velocity of 4 meters per second. Somebody else tell me the next thing.
14.
13 seconds. And 13 seconds.
Alright.
Okay, tell me the next thing. Dakota. Oh, did you have your hand raised? Dakota, I called on you. Someone will call on her and say, yes, go. Okay, how far? Let's stop it at how far, okay? That's great. This is a very confusing question because a lot of students misunderstand what the term how far means. Because how far and how long, specifically how long, is a really confusing way of asking a question because you can ask for how long for time and distance. How far is only distance. How long can be time or distance, so you really have to look at the contextual clues to determine what they're asking. Okay? This one's not so bad, actually. So how far, what's it asking? If I ask, how far is it from me to the wall? What am I asking there? I'm asking for the distance, right? Okay, so a train accelerates from a velocity of 4 meters per second to 27 meters per second in 13 seconds. How far did the train travel in a given time? Okay, so what I want you guys to do is start the problem. You guys are doing this one on your own. Ethan, yes?
So, you had a question where, like you said, if you can't get how close you to the wall, do we assume the closest spot to you to the wall or the farthest spot to you to the wall?
The closest. Okay, so, good question. Okay, guys, get busy on it. Yeah, in your journal. You don't have to write the question, just do the guess. Just start setting it up. And just for future reference, whenever I grade these, if I decide to grade them, I don't grade them all that often like this. But this is the generic way I decide to grade whenever I'm just asking for one question a lot of times. That's for something else. That's for the diagram. You never include friction on kinematics because we're not there. Okay, so being able to put the guess method down, just writing the guess method down is worth 20%. I don't know why that's still doing that. Okay. Just putting the guess method is 20%. That's a pretty nice little bonus, right? For telling me the given and the unknown, that's another 20%. For working out the problem and doing the substitution, that's 40%. And that leaves 20% for having the right answer. Does that make sense to everybody?
Yeah.
So if you get the wrong answer, what did you get on as a grade? You got a B. You got a B. Just for putting guess down and writing down what you know and what's unknown, you get 40% just for doing that alone. Okay? And then this area right here, that's not an all or nothing. Okay? There's definitely subjectiveness to it by me, but it's not all or nothing. Okay? These things are all or nothing. The guess method, writing it down, is an all or nothing. Okay.
Is it initial minus velocity over 2? Initial minus final over 2? Or is it final minus initial?
On what?
On, like D equals...
What are you, I don't understand what equation you're trying to use.
Never mind, I'll figure it out.
Okay.
Oh, it's distance over time. No, it's not distance over time.
Which A are you talking about? Is it my bad handwriting?
No, on the formula.
On VAVG. AVG is average.
Yeah.
Yeah. A is normally acceleration.
So this is
Yes.
why are we doing average velocity for this one?
Why are we doing average velocity for this one? Because we're low on time. Let's look at this. Okay, we are low on time, and I got one more thing I got to show you. Okay, so the unknowns, or sorry, the knowns. Our initial velocity is 4 meters per second, right? Our final velocity is 27 meters per second. Our time, that's delta t, is equal to 13 seconds. And our unknown is our delta d, right? So the equation that we're going to use, though, that's harder. A lot of my students went right to these two equations right here. They recognized there was not acceleration given. So they said, okay, I can find acceleration. Rightfully so. You can get acceleration by solving that equation right here. Okay? And then you could plug that acceleration into this equation and back out delta d. Okay? However, that's not a simplistic way of doing it. Okay? A simpler way is to find your average velocity. So your average velocity formula is equal to V naught plus VF over delta, over 2, right? Does that make sense to everybody? Over 2. So, it's kind of like if you have a test, or I had a test the other day, a teacher test. I'm totally lying about this, by the way. So many people think I failed the teacher test. I did not. If I made a 50 and I retook it and I made 100, what's my average?
50.
No.
I'm going to use your average way of doing it. 75. Yeah, 75. So that's all you're doing. 4 plus 27 is 31 divided by 2 is what? 30 divided by 2 is 15. 1 divided by 2 is a half, so it's 15.5. So, the average is equal to 4 plus 27 divided by 2 is 15.5, and that's going to be meters per second, right? But we're not done. That's just the average velocity. It was asking for how far did the train travel. Well, the formula for average velocity, another formula, there's 2 of them, is what? Somebody say it so it makes me sound smart. Delta D over delta T. What are we looking for here? What's it asking for? It's asking for how far, right?
Whoa.
So we're going to do what?
Multiply by delta D on both sides.
Multiply by delta T on both sides. Delta T. Wow, that doesn't work.
Interesting.
Delta T. Delta T. Delta T divided by delta T is 1. So now we got to multiply 13 seconds times 15.5 meters per second. What happens to the seconds? That's on bottom, that's on top. What do? Little dimensional problem here. It's a V. What happens to the seconds, guys? Let me do this a little differently because you guys can't see it as well. Okay, so let me do this just a little differently so you guys can see it better. That's seconds over 1, and this is meters over seconds. What happens to them? They cancel to 1, right? I'm not doing that again. 201.5 meters. Now, here's another little trick. How many sig figs should we show? 2. So that actually becomes, you have to put it in scientific notation, so your answer is 2.0 times 10 to the second power. Put 1, 2. That number got smaller, this number has to get bigger. Okay. So let me tell you about one more thing. On Monday, oh, you know what? On Monday you have a lab report that you'll have to write, so you'll need to go out to Google Classroom and look up that lab report on how to write. Okay, get out this sheet. No, don't worry about that. Don't worry about that. We didn't get to it. Okay. Well, you would have had a hard time finding those videos. It was videos you were supposed to make in class.
Hello.
Let's look at number 2. Okay. 10 newtons down, 10 newtons up. 15 newtons, 5 newtons. Okay? So some of the forces in the x direction, some of the forces in the y direction. Some of the forces in the y direction. Let's do that one because that's easier. 10 newtons plus a negative 10 newtons. What's that going to equal? 0. Negative 15 newtons, doesn't matter which one you do first, plus 5 newtons, what's that going to equal? Negative 10 newtons. It's a what? Yeah. The math? The math, yeah. Yeah. You're always going left to right. Notice you're always adding everything. Sometimes you just have to add a negative number. Guys, on the back right here, you're working these just like you do the particle method. Okay? It's just they give you boxes. On this, I know some of you guys are having problems with vectors. Still having problems with vectors, so let me show you something. Let's say that I'm adding these two vectors up. And one of them's like this, and one of them's like this. This is the head, that's the head, this is the tail, that's the tail. Say it with me, head to tail. Head to tail. This is the resultant. Now, doesn't matter. Head to tail. That's the resultant. It's always going to be the same magnitude in the same direction. Doesn't matter which one you put where, same resultant. Okay? So it doesn't make a difference. Yes. No, that was what I was just talking about is for this one. This one right here, it's just like the particle method. These right here is what we did in class today. This is due Monday when you walk into class. Also, when you walk into class, we have a lab to do. Okay? So, one thing I want you guys, please don't get up yet. Please don't get up, Ethan. Guys, I still have like a second. You need to go on Google Classroom and look over the lab report. You guys are going to be doing formal lab reports on Monday. Okay? There's a rubric, and on that lab report, you need to go through each section, so that way you know exactly what will be expected of you. Okay? Let me see if I can find it real quick. Okay, so this is out on Google Classroom. It's up underneath course information, right here, information and common links. Make sure you go through this over the weekend and you're familiar with it, because if you're not, you're going to be really lost in a 45-minute class on Monday while you're doing a lab. Okay? Is there any questions? Okay. That's not an okay to leave the classroom. That's an okay to put your stuff away. Fine.